Last thing we're going to do here is talk about a very interesting phenomenon that's called Lenz's law. And this is one of my favorite principles or properties in all of physics. And it's just very subtle and very beautiful how it works. But before we get into it, let me tell you about one thing I forgot to mention, which is there's another right-hand rule, and that's for coils. So let's imagine I've got a coil of wire here, and then I'm going to hook it up to a voltage source, as we did. What we know is that this coil of wire is going to create a magnetic field. There's actually a right-hand rule for coils that tells you the direction of the magnetic field for that coil, and here's how it goes. Of course, you need access to your right hand, right? What we need to do is we need to figure out which way are the coils going. So which way is the current going through the coil? So here's the positive charges that are going around this coil in this direction. So this coil has current that's going in this direction, I like that. And for this right-hand rule, I take my fingers and I curl them around in the direction that the current is going, and then my thumb points in the direction of the magnetic field. So fingers curl for the current and thumb points in the direction of the magnetic field. So this coil right here would have a magnetic field that points up towards the camera, towards where you are. So the magnetic field points up. Remember, a magnetic field is going to tell you which way a north magnet would feel a force. So if I had my string sandwich here, which got stuck to another magnet, okay, good. I think that we said that the purple face here was north, or you're seeing blue, that if I have it hooked up as such and the current's going around this direction, then this north magnet would feel repelled, and this south side of the magnet would feel attracted there, clunk, right? If I reverse the current and the current's going in the other direction, then I would curl my fingers this way and my magnetic field would go down, in which case the other side of the coil, the back side of the coil, would be where the north magnet would feel repelled by, and so it would flip which way this string sandwich would feel a force. So that's just something interesting to know, that there's a right-hand rule for the direction for coils. Okay, so let's talk about what Lenz's law is going to do. Lenz's law is really, really interesting. What we saw in the last video is that if I have a coil and I take a magnet and I move a magnet near the coil back and forth, I actually create a current in this coil. So that's actually, let's get rid of that for a sec. Okay, we'll get rid of the right-hand rule. There we go. So we'll use that right-hand rule in a minute. So once again, if I have this coil and I move a magnet near the coil, then I'm going to create a current. And we had the galvanometer, and we saw in the galvanometer that the needle went. But what's really interesting here, though, is that if I have a current in a coil, the coil also creates its own magnetic field. So I use a changing magnetic field to create a current, and then the current that's in there also creates its own magnetic field, which is totally fascinating. And it turns out that the magnetic field that's created in this coil is going to actually oppose the original magnetic field. So if I'm pushing this magnet in this way, remember, it's got to be a moving magnet. Holding the magnet here is not going to do anything. If I push this magnet this way, it's going to create a current in this coil such that the magnetic field of that current opposes the original current. And that's known as Lenz's law. So here it is written out. Lenz's law says that the induced current in a loop of wire creates its own magnetic field, and that opposes the original changing field. Here's my loop of wire, right? If I induce a current in there, how do I do that? Well, electromagnetic induction, I have to move a coil near a magnet, or move a magnet near a coil. That's going to create current in this coil. That current in the coil creates its own magnetic field. We know that. We know that putting current in a coil creates a magnetic field. And that new magnetic field is actually going to oppose the original magnetic field. And there's some pretty cool things that can happen if you sort of exploit this property of Lenz's law. So I'm going to try to show one to you. And I made a recording here on my phone so that it could be a little better definition. And what I have here is a very strong magnet. This is a very strong, big neodymium magnet. And then this is just a big, large chunk of copper. So a huge chunk of copper and a really strong neodymium magnet. Now, copper is not ferromagnetic, so this magnet should not be attracted to or repelled by the copper. It sort of doesn't really care about it. What's going to happen is I'm going to reach in here, The magnet is actually suspended on some strings, and sorry, this is in slow-mo. So I'm going to reach in, I'm going to grab the magnet, and I'm going to swing it back, and watch what happens when it falls toward the copper. This is so fascinating. I'll show you this in person as well, but I wanted to make sure that you had a chance to look at it because Lenz's law is so interesting. So it's going to swing back towards the copper, and then zoop, it stops. So it does not make contact with the copper, which is so fascinating. It's almost magical how that goes. Here comes my hand again. I'm going to lift it up and swing it. Sorry, it's slow-mo. Swing it back towards the copper, and watch carefully. It's actually not going to make contact with the copper, but it is going to come to a stop. And you might be like, well, that's fine, it's magnets. But remember, copper is not ferromagnetic. So copper and magnets don't really care about each other, right? There should not be a repelling or attracting force, but somehow it's being repelled. It's very, very interesting what's happening here. So pulling this back, again, scooch it forward. Here it comes. So what do I have here? Well, I have a moving magnet near what could be thought of as a very, very thick wire. One really thick, very, very conductive wire. When this magnet moves near this piece of copper, it actually induces current in the copper. So there's current that goes around and around in a circle in the copper. If I have current in a piece of wire, once again, you can think of this as one huge, big, thick piece of wire. Current in a wire creates its own magnetic field. And Lenz's law says that that magnetic field opposes the original changing magnetic field. So once again, this moving magnet creates a current in the copper. That current in the copper creates its own magnetic field that repels this original magnetic field. And it's pretty amazing. Like I said, I'll show you in person, but I thought I would also show you on video just as a preview. Let's see if I can scooch it forward a little bit. Try it one more time. Here it goes, swinging towards the copper, and shoop, just stops, just like that. Fascinating. All right, so once again, that's having to do with Lenz's law. The induced current in a loop of wire creates a magnetic field that opposes the original changing field. Okay, hope that was fun for you.